Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. We will be doing lecture number 26 here, and the topic of the lecture will be Introduction to Semiconductor Heterostructure part 2. The first one was part 1 and this one is part 2, and we will start from where we left in our previous discussion. So, the outline here again the same thing remains as the first one, and we will be now looking into the ohmic contacts and the Schottky contact and try to give you an idea about Schottky effect, right. So, it is also known as image force lowering effect. So, barrier lowering IFBL, we will look into that, but before that we will first make understanding of the energy band diagram from where we have left in the previous lecture. So, if you remember in the previous lecture we were basically making a metal semiconductor contact, and we were saying that there is a built in potential, there is a electron affinity concept, and there is a work function, right. Now, let me take up metal semiconductor contact and show to you that. So, this is a metal semiconductor contact which I am referring to. So, let me assume this to be as x equals to 0, and this is my Fermi level for the metal, then this is my vacuum level, let us suppose. Then this is q times phi b 0, right, and this is the ideal barrier height which you will see. Now, if you apply a reverse bias, it primarily means that you are forcing the energy band onto the right hand side, which is the semiconductor. So, this is the n type semiconductor and this is metal. So, this side you are forcing it to go down, and what will happen therefore in this case is that this will go further down like this, right, and the Fermi level will be somewhere here, valence band will also go like this. So, there has been a dip here, and this distance or this energy level will be referred to as q v built in plus VR, where VR is basically the reverse bias which you are giving on the semiconductor side. So, on the semiconductor side whatever voltage you are giving, positive voltage, that will pull the energy band diagram on towards the semiconductor side below, and the Fermi level will also show a shift. So, this is the effective Fermi level shift which you see for the metal and semiconductor. This is the effective del EFM which you see on the metal and semiconductor, and this is the valence band which you see. This is not go down, but it will go like straight like this, right, it will go straight like this. So, what happens is my effectively the width actually x equals to xn. So, the width from x equals to 0 to x equals to xn is basically the depletion width, and as you can appreciate that the depletion width will actually go on increasing as you make the metal semiconductor or the semiconductor potential go higher and higher, and it dips, it forces the energy band diagram to go down on towards the metal side. However, if you take up in the forward bias condition, if you take up, then this is the sort of a reverse bias condition, and if I take a forward bias condition, then this is x equals to 0 which you see, right, and then this is my vacuum level which I am assuming. This is the Fermi level vacuum level EF EM, and this is q phi b 0, ideal sort of a barrier height. And then what happens is that because of the forward level, maybe slightly this will be bent slightly like this, right, and there will be Fermi level here. This will be also slightly bent like this. So, this is your EV, EC and EF, this is your vacuum level, right, this is your vacuum level. And therefore, you can see the point where the energy band diagrams are constant, this is x equals to xn has been reduced. The depletion weight, this is WD, this is the WD value, right. And this is the WD value for a forward biased PN junction, which is actually reduced, right. Now, an exercise for you to understand is why we say that the edge of the depletion is where the potential is constant, right. As you can see here, if you look at either this point or at this point, in both the points we refer to that edge where the potential is constant. where after which the potential is constant. Potential is constant primarily means what? That it does not vary with respect to distance, and which effectively means, and this is quite interesting, which effectively means that if my dV dx is equals to 0, it implies that my V is constant and therefore my electric field is 0. So, beyond the depletion region, the electric field is actually equals to 0, right, and that is the reason you say that this is the point where the depletion edge actually occurs, right. As you can understand, there will be no electric field on the metal side, and similarly there will be no electric field parallel to the interface between metal and semiconductor, because that is not the point where the electron anyway flows. So, whatever electric field will be towards the semiconductor side will be past the point where your potential actually becomes independent of x, right, that is the point. So, that is the edge we say as the edge where your depletion thickness width has been extended. Same things for the forward biased p-n junction, in this case metal semiconductor, n type semiconductor there. Again I am leaving as an exercise to you to do the p type and metal semiconductor, metal contact. Please try to do this part as well, right, and this will be quite interesting part which we will see. So, typically where do you see such contacts? You see these contacts when you are having the semiconductor and the metal. For example, if you take up a p-n junction diode, let us suppose you take up a p-n junction diode here, then this is n, this is p, let us suppose, then there will be a contact here which will carry the current forward, there will be a contact here which will also carry a current, and there will be a bias, sort of bias applied here in the forward bias. So, this is what is known as a metal semiconductor contact. This is MS contact, this is an MS N type contact, this is an MS P type contact, right, and this is where you will have barriers available to us. Now, the idea here is that higher the barrier height, lower will be the current, which we all know for sure in all the cases, and that is the reason the work function difference plays a very critical role in understanding the values of this thing. Now, we write down this potential, the vacuum, this one, to be equals to Q times V built in minus V, say forward biased, or V0. So, quite interestingly, the overall barrier height actually reduces in application of bias which is forwarding it. If an n type, if it is an n type semiconductor negative bias, then the barrier height actually starts to reduce, and as you can see, the conduction band edge moves closer towards the vacuum, and you can easily therefore plug the current there. Whereas in the first case, when you are applying a reverse bias, you are actually making the conduction band go well below the vacuum level, and as a result effective barrier height on the semiconductor side was increasing drastically. Please understand, the semiconductor barrier on the metal side does not change, it is still Q times phi b 0, where phi b 0 is the ideal metal side semiconductor. Now, the obvious question is why it does not change drastically in the metal side, right. Please try to understand this question, please try to yourself give an answer to the question why on the metal side you do not see a drastic change in the value of your Fermi level when you apply a bias. Please understand, you are applying a bias only on the semiconductor side, you are not applying a bias at this stage on the metal side. So, this gives you a basic understanding of the metal semiconductor contact and its overall characteristics. Let me take up an ideal junction and show it to you, which means that I take up a p-n junction or even an ideal junction, and we see where the depletion edge is with respect to the electric field available within the device. So, if I take up an ideal junction now, so let me take up an ideal junction. Then we can write down in an ideal junction that dE times dx, dE dx is equals to minus rho x by epsilon s, Gauss law. This is basically a volume density of space charge, right, per unit volume by epsilon s, which you get here as dE dx. Therefore, if you integrate on both sides, then I get E to be equals to integral Q times Nd, where Nd is the donor impurity, divided by epsilon s into dx. So, what I did, I took dx to the right hand side and then I integrated rho x is basically the charge density, volume charge density, that can be written as Q into Nd, where Nd is the number of donor impurities per unit cube, and then you multiply that with Q and you get the total charge divided by epsilon s into dx on this side gives you this value, which approximately comes out to be equals to Q Nd times x by epsilon s plus C1. Now at the edge, obviously E will be equals to 0, and therefore I can write down C1, the boundary condition C1 can be written as Q times Nd into xn, the depletion width, upon x epsilon s. Therefore, if you place now back into this expression, then I get E equals to minus Q times Nd divided by epsilon s into xn minus x. What is xn? Xn is the edge of the depletion, right. Now, as you can see, when x equals to xn, right, this quantity goes to 0, electric field is equal to 0, which is mean the edge of the depletion, the electric field will be equal to 0. When x equals to 0 means at the surface of the metal semiconductor, x equals to 0 implies that you will only have at x equals to 0, therefore, E will be equals to minus Q times Nd psi Sn times xn, right. This is at x equals to 0, which means that if you plot the electric field plot on the semiconductor metal side, then it comes something like this. This is my semiconductor, this is my metal, obviously it will be negative and the electric field will be in this direction. This is semiconductor, this is my interface. This is my, so at interface electric field is equals to maximum edge of the depletion region, it is exactly equals to 0. If you try to find out the width, which is the width of the depletion region, which is W, and it is given as xn, then this is also written as 2 epsilon silicon V built in plus Vr in case of reverse bias divided by Q times Nd to the power, which means that the width of the depletion region on the n side is actually a parabolic function of the bias which you give. Make it 4 times your reverse bias, your width will increase by approximately 2 times, right, and this is what happens when you do a metal semiconductor n type, in this case n type semiconductor contact which you want to do it. So, these two expressions, this one gives you the expression of electric field within a ohmic contact, and this gives you the width of the depletion region on the n side in case of a contact, right, and these widths are therefore dependent on the value of doping concentration as well as dependent on the value of the applied bias. Higher the bias, more will be the width, higher the doping concentration, less will be the width, right. So, that is that you can appreciate therefore that. So, if you go back to your previous discussions, for example, in this one, and if you are doing a reverse bias condition and the doping concentration on the n side is very high, right, say it is near degenerate, then this width will actually reduce drastically, this WD will reduce, this will move somewhere to the left of it, right. So, one thing which you should be aware of, that under high doping concentration, under high doping, so the I want to just write down here, high doping effectively means that the width of the depletion on the n side will be as small as possible. Higher the doping, lower will be the width available to me on the n side. This gives you a brief idea about why you see a reduced electric field onto the n side when your doping concentration is relatively small. Now, let me also show to you about this particular point, that so this is the edge, right, this is x equals to 0 and this is x equals to xn. At xn you will get 0 value, at x equals to 0 you will get the maximum value. On the metal side, of course, the electric field has to be 0 because there is no movement of charge carriers on the metal side. With this knowledge, let me showcase to you one small numerical problem which will help you to understand what we are doing at this particular stage. This is basically a question. So, I assume I have a metal n type semiconductor available to me, right, and obviously I will assume that the value of the doping concentration donor traps is 10 to the power 16 per centimeter cube at 300 Kelvin, right, and you have, let us assume that the metal is basically a tungsten, and then you have this n type silicon on this side, right. And therefore, we already know for tungsten metal function is 4.55 volts. This is a standard sort of value which you get from experimental observations, and chi of silicon is approximately 4.01 volts approximately. So, the question is you have to find out the barrier height, right. So, if you look at the ideal barrier height, therefore, phi b 0, it can be written as phi m minus chi. So, what I will find out is 4.55 minus 4.01, and that gives 0.54 volts. So, if you want to convert this into energy, you know that you have to multiply this with Q. Q times V is basically your energy. So, what I am showing you is just the potential. This you have to multiply with 1.6 into 10 to the power minus 19 in order to get in terms of energy, and that is the reason we say phi b 0 is this much. Now, let me write down phi n or V built in, phi n, and this phi n or V built in is kT by Q, ln of Nc by Nd, and therefore, this comes out to be 0.0259 millivolts. Ln of Nc is 2.8 into 10 to the power 19 divided by 10 to the power 16. So, Nc is a constant value which is available to you. Nd is already given you as 10 to the power 16. If you solve it, you will get this to be is equals to 0.206 volts. So, if I write to find out V built in, then V built in will be phi b 0 minus phi n, and that is phi b 0 is 0.54 minus 0.206. This gives you the value of 0.334 volts as the value of V built in. So, what is the V built in? Therefore, this much amount of voltage, if you multiply this with Q energy, will be required for an electron to cross over and come towards the metal side. So, let me find now the edge of my depletion Xn, and it is given as 2 epsilon silicon V built in divided by Q times Nd into to the power half. If you put all the values, it comes out to be 0.208 into 10 to the power minus 4 centimeter, and therefore, you can get E max, which is the maximum electric field, given as Q Nd Xn by epsilon silicon. Again, you will get 3.21 into 10 to the power 6 volts per centimeter, which is at the edge of the metal semiconductor contact, right. So, this gives you the effective value of the E max electric field. So, this is one part of the answer. Another part of the answer is this one. So, these two are the important answers, that we gave V built in to be equals to 0.334 volts, and I get E max or the maximum electric field at the interface to be equals to 3.21 into 10 to the power 6 volts per centimeter, right. And this electric field is negative in nature within the semiconductor, because we have seen it in the previous slide that you see this is negative in nature. It cannot be positive. Negative why? Because right, it is just opposite direction of the voltage which you apply, and that is the reason it is negative in nature, right. Now, what we so this was the ideal junction. Ideal junction primarily means it is perfectly clean, the junction is perfectly clean with no impurities added to it, and there are no issues available there. Now, if you want to find out capacitance per unit area for this metal semiconductor contact, then it comes out to be C prime to be equals to Q times epsilon S Nd divided by 2 times V built in plus Vr to the power 1 by 2. This is my C prime. C prime is capacitance. Why capacitance per unit area? Why is it capacitance? From where the origin of the capacitance is? Well, you can see that there is a depletion region, right, which will be formed by application of a bias. This depletion region will therefore separate charge carriers from each other, and therefore, we say this to be as capacitance per unit area sort of concept, right. C prime we say, which is Q times epsilon S Nd upon 2 times V built in plus Vr. Now, if you do one thing, and this is where we try to find out the value of Nd methodology, we do 1 by C whole square. This comes out to be equals to 2 V built in plus Vr divided by Q times epsilon S times Nd, and therefore, if you plot if you plot on the x axis 1 by c square prime versus VR, right, then you will see that very interestingly this can be broken up into two parts. One part is basically 2VB built in divided by q times epsilon s times nd, this is a constant term, and plus 2 times VR divided by q epsilon s nd, which is depending on the value of r. So, it is basically y is equals to mx sort of plus c sort of straight line equation which you will get, right, and the cutting of the straight line where they will cut the y intercept is basically the value of, this is the y intercept which you get, and this is the slope of the line which you get. So, from the slope of the line I can extract the value of the doping concentration, which means that, let me draw for you maybe one or two, maybe say this is for silicon, tungsten silicon. Tungsten is the metal side and silicon is this thing, and let me draw for tungsten gallium arsenide. So, this is tungsten gallium arsenide junction, right, and this is VR equals to, this is 0. Now, when you place VR equals to 0, then the right hand quantity vanishes and you are left with 2 built in upon q epsilon s into nd as the value of your 1 by c bar square for both the cases. And when the value goes on changing for the reverse bias, you see a change here because of the nd change taking place here. Now, typically as you can see from the slope of the graph, if you want to extract it, then you will get m to be equals to 2 by q epsilon s nd. So, if you can extract the slope, since you know the value of all these quantities, you can extract the value of nd, right, and this was what we were trying to say, that if you can extract the value. So, this is a methodology by which you can extract the value of the doping concentration on the metal side, right, and this is the methodology which we do. Now, let me come to the discussion on the basic. I will add here and then we can move ahead. This is known as a Schottky effect, right, also referred to as a image force induced lowering or a barrier lowering effect, IFBL, image force barrier lowering, IFBL we refer to in the second order effects which comes into picture, and I will explain to you from where we got this concept here. So, what we will do is we will discuss this one later on. Let me come to this slide which will be easier for you to understand. So, when a metal makes a contact with a semiconductor, obviously at thermal equilibrium they should be in coincident with respect to each other. However, when you apply, so relative to the Fermi level in the metal, the Fermi level in the semiconductor is lowered by an amount equal to the difference in the two work function. I hope you understand this particular point. However, one important point comes into picture, that let us suppose I have this, I will take up in the next class in much more detail, but I will just introduce to you and we will leave here, that let us suppose this is a dielectric and I have an electron fixed in the dielectric, right, available to me. Then there will be some electric lines of forces which will be emanating in this manner, right, this manner. There will be electric lines of forces which will be emanating and they will be perpendicular to the dielectric interface. So, what we can do is, on the metal side we can put a positive side in order to just make it continuous line flow, and because of this there will be effect, though there will be no net electric field, but conceptually I can say there is an electric field because there are two charge carriers which are separated by a distance x. So, if this distance is x, right, let us assume that this distance is also x. So, the total distance is 2x and therefore, I put 2x here and I get q square by 16 pi epsilon 0 x square here as the force. So, this is a force which, by the virtue of the electron being at the place where it is, it creates a force onto the metal side which tries to lower the barrier, right, and that is known as the Schottky effect or Schottky barrier lowering effect. We will come to that in the next class. So, what we have learned in this class is we have learned about two important points. One is we have learned about the values of this metal contact, this contact here. We learned into forward and reverse how we are looking into the Fermi level diagram for metal semiconductor contact, we saw that the electric field will be 0 at the edge of the depletion, maximum at the edge of the semiconductor junction. We also then for ideal junction we saw how the electric field will linearly vary with respect to space in the depletion region, and we found out the value of the maximum depletion width at the and this thing, and we saw that higher the doping concentration, lower is the width. We gave you a numerical example to showcase to you the value of Emax and VBI, and finally we saw what is the meaning of capacitance in this case and how doping concentration can be extracted from this capacitance. When we take up the next class, we will take up the image force barrier lowering effect in much more detailed manner, right. Thanks a lot for your patient hearing.